Something extraordinary is unfolding in astronomy right now, and most people still don't realize how deeply it is reshaping our understanding of reality. The James Webb Space Telescope is no longer just confirming existing theories. It is pushing against their limits, exposing gaps in what we thought we understood, and revealing a universe that behaves with far more complexity than our models ever allowed. What makes this moment so unsettling is not a single discovery, but the accumulation of many. Each one, on its own, might be explainable. Together, they begin to form a pattern that feels less like coincidence and more like a system we have not yet learned how to read. One of the earliest cracks in this framework comes from an unexpected world, TOI 4507b. On paper, it is a gas giant similar in size to Jupiter. In reality, it should not exist in its current form. Its density is far too low, as if the planet has been inflated beyond physical limits, holding together something that should have collapsed under its own gravity long ago. Even more puzzling is its orbital geometry. Instead of moving in a stable, aligned path like most planets, it travels at an extreme tilt, nearly perpendicular to the rotation of its star. This kind of orbit suggests violent gravitational history, yet there is no clear evidence of what could have caused it. James Webb's atmospheric readings are now trying to decode why this world remains so strangely unstable, but the deeper implication is already clear. Planetary formation is not as predictable as once believed. If strange planets were the only anomaly, it might still feel manageable. But James Webb has also pushed into the early universe, and what it found there challenges time itself. Supermassive black holes, hundreds of millions of times the mass of the Sun, appear fully formed less than 600 million years after the Big Bang. According to standard cosmology, that should not be possible. Black holes are supposed to grow gradually, over vast stretches of time. Yet here they are, fully mature, sitting in galaxies that should still be in their infancy. This suggests either an unknown rapid formation mechanism or something far more radical, that the early universe evolved faster than our equations can describe. Closer to familiar territory, Webb has examined worlds that seem almost impossibly extreme. WASP-18b, for example, is a gas giant locked in an orbit so tight that its atmosphere is pushed to thousands of degrees. At those temperatures, molecules break apart instantly. And yet, Webb has managed to construct a three-dimensional map of its atmospheric structure. Winds move at supersonic speeds across its surface, redistributing heat in patterns unlike anything seen in the solar system. What was once an abstract exoplanet is now a physically mapped world with measurable atmospheric dynamics. It is no longer just a point of light, it is a functioning, unstable system. Even more surprising is TOI 561b, a super-Earth orbiting so close to its star that it should have lost its atmosphere entirely. According to previous models, radiation from the star should have stripped it bare long ago. Yet Webb detects a surprisingly stable atmospheric layer. That single observation forces a difficult question. If atmospheres can survive where they are not supposed to, then how many dead planets are actually still active in ways we do not yet recognize? This question becomes even more pressing when we step back and look at the early universe again. Webb has identified galaxies that appear fully structured only 100 to 200 million years after the Big Bang. Spiral arms, mature formations, organized structures, appearing far earlier than standard models allow. In addition, ancient supernova events have been observed dispersing heavy elements much sooner than expected, seeding the cosmos with the raw ingredients for planets and chemistry at an accelerated pace. The universe, it seems, did not wait patiently to evolve. It moved quickly, almost aggressively, toward complexity. That idea becomes even more unsettling when we consider planets surviving conditions that should destroy them. Worlds orbiting neutron stars and pulsars, objects created in violent supernova explosions, appear to have endured radiation levels that should sterilize any surrounding environment. And yet, these planets remain intact, some even showing signs of atmospheric retention. This suggests planetary resilience far beyond what standard models predict. It also forces a rethink of what uninhabitable really means. Across many of these discoveries, a pattern begins to emerge. Webb repeatedly finds atmospheres that should not persist but do. It detects chemical combinations, like methane and carbon dioxide coexisting, that should destroy each other over time but continue to appear together. These disequilibrium states suggest constant replenishment, either from geological processes, internal planetary heat, or something even more complex. Whatever the cause, these worlds are not static. They are active, self-sustaining systems. This forces a major shift in how we define habitability. For decades, scientists focused on a narrow, Goldilocks zone, a thin orbital band where liquid water might exist. But Webb's discoveries show that habitability is not a single location, it is a spectrum. Some worlds protect oceans beneath ice. Others trap them under thick atmospheres. Some endure violent stellar environments, while others remain stable for billions of years under quiet stars. The conditions for complexity are far more flexible than we once believed. Perhaps the most important realization is not about any single planet or galaxy, but about repetition. These anomalies are not isolated. They appear across different systems, different star types, and different cosmic environments. That repetition suggests underlying principles we have not yet identified. It suggests that the universe may not be randomly chaotic, but structurally biased toward creating complexity whenever conditions allow it. This does not confirm life beyond Earth. But it does something just as significant. It shows that the building blocks of life are not rare exceptions. They are widespread, persistent, and resilient. Chemistry does not wait for perfect conditions. It adapts. It continues. It finds pathways through environments once considered impossible. When all of this is placed together, strange planets, early galaxies, resilient atmospheres, extreme survivability, and persistent chemical imbalance, a new picture begins to form. The universe is not fragile or static. It is active, evolving, and far more efficient at producing complexity than previously thought. And that leads to the most uncomfortable realization of all. The question is no longer whether life exists elsewhere. The question is how often the universe builds conditions where life becomes possible, and how many of those we have already overlooked simply because we were not looking closely enough. What James Webb is revealing is not a final answer. It is a transition. A shift from speculation to observation. From rarity to abundance. From simplicity to layered complexity. And as more data arrives, one thing becomes increasingly clear. The universe we thought we understood is only a small fragment of a far larger, far more dynamic reality. And this may only be the beginning.